Just a second. I have to prep the event intro. One thing I forgot. Hey everyone, welcome to the February meetup for Tulsa Lambda Lunch. Thank you all for coming. We're here thanks to Techlahoma, our volunteers, and our speakers. Techlahoma is a non-profit volunteer-run organization that puts on 39 groups, 2 conferences, and sponsors free local events. We do this all to support our mission to advance the grassroots tech community of Oklahoma. Learn more at techlahoma.org. It's extremely important to us that our members feel safe and respected at our events. If you have any issue with someone's behavior at a Techlahoma Foundation event, please let us know via the incident report form or one of the other methods provided on our website so we can take immediate action. If you'd like to get more involved with Techlahoma, go to help-wanted.techlahoma.org to find ways that you can volunteer. If you want to support Techlahoma, you can go to techlahoma.org/donate and sign up for a monthly subscription. 36 Degrees North donates the space for us to meet. They also offer free workshops as well as co-working desks and offices for a monthly fee. You can find more info at the front desk. And finally, thank you to Tech Systems for food. All right. One additional announcement is March is going to be our last month here in this space. So starting in April, we'll be in another space. I haven't fully determined what that is, so keep an eye out for the location on the meetup announcement for when that changes. But I should be able to announce where that will be during March's meetup, so be here in March, or at least watch the meetup. All right. So what if I told you that you can take an HTTP REST API and scale it automatically without limit? Okay. So today's topic is pure FP web apps in AWS Lambda using Http4s, because I couldn't come up with a shorter title than that describes what it is I'm trying to do. So our logos here this is the CATS logo, isn't it cute? FS2 is the Http4s, and this is the AWS Lambda logo. I just wanted to show that off because I thought they were all neat. All right, so let's do before we get into the AWS Lambda parts or even the Http4s parts, let's do a quick functional programming conceptual refresher here. So let's talk about pure functions, effects, and specifically, importantly, today's topic, the Kleisli arrow. So pure functions, in my mind, are like a mathematical function. They have some input, they have some output, nothing else happens. So as Wikipedia says, a function is a process or relation that associates each element X of a set X, the domain of the function, to a single element Y of another set Y, possibly the same set, the codomain of the function. But what that really means is this. So we have some grouping X that maps to something in Y. More than one X can map to the same Y. There can be things in Y that aren't mapped, but everything in X maps to something in Y. So it's total. It is pure in that nothing else happens besides a mapping between two things. Questions? And feel free to interrupt me at any time. I like a more interactive kind of presentation. So if you have questions, don't be afraid to stop me. All right, referentially transparent. An expression is called referentially transparent if it can be replaced with its corresponding value without changing the program's behavior. So a pure function has to be referentially transparent. And here's an example of what that means. So I have this function add2. So it takes some integer and literally just adds 2. You can see, very much like a mathematical formula, it doesn't do anything special other than math. So if I take add2 twice here, it adds it to 8. If I take add2, I get 4. And if I take this value here, and I just add it twice, just like I'm doing here, I'm replacing the function calls with their value, given the same input, I get the same output. You can see that add 2 twice is the same as add 2 twice part 2. Here's a counter example. So if I have add random, that just takes I and adds some random value between 0 and 10 to it. If I do that twice, I end up with, in this case, 17. All right, if I just do it once and then replace the 2 calls to it with that initial value, I get something entirely different. So this function is not referentially transparent. Every time I call it, I get a different result, even given the same inputs. So this function is not pure. Any questions? Okay, so effects. They're anything other than just warming your CPU up. So we talk about I/O, which is, you know, network or display or file or disk or database, etc. So that's what an effect is. And obviously we wouldn't do anything if we didn't have some sort of effects, right? We really don't want to just warm up the CPU. So in functional programming, we want effects, but we want to avoid side effects. So side effects in computer science, a function or expression is said to have a side effect if it modifies some state outside of its local environment. That is to say, has an observable interaction with the outside world besides returning a value. So our good old add random function was one that had some sort of side effect, in that it was getting some randomness from the machine state, and that was its interaction. All right, so here's an example of a side effect. We're just printing every time we add 2, which is not a desirable effect. So the reason why I'm bringing all this up, though, is because we're going to be talking about AWS Lambdas, right? So we're talking about a way of executing functions in the cloud, and we need a way of encoding our side effects in there. So we'll see a little bit more later. So the last conceptual refresher here is the Kleisli arrow. Does anybody know what the Kleisli arrow is? That's okay, I didn't know for the longest time either. All right, so before the Kleisli arrow description, let's talk about function composition. Everybody's seen the old fog-goth business, right? So we have a function of A to B, and we have a function of B to C. And if we compose them together, we have a function of A to C. So we have 2 ways of composing that in Scala. We can say G compose F, which reads a little harsh, or we have F and then G, which I think reads better. So we take F, and then we take its value, and we pass it to G. Pretty straightforward. All right. Now, how many people were here for my F et al. Talk, where we talked about side-affecting behavior and wrapping them in an I/O monad? Does everybody kind of remember that? Okay. So we have an I/O type. We have a function from A to I/O of B. I don't really care what it does. We have some function of B to an I/O of C. So these are functions that have an effect that we're encoding in our type system. Well, unfortunately, with just classic function composition, I can't just take F of E and compose it with G of E because we have a type mismatch. The B we're expecting here, we're getting an I/O of B. So the way we solve this problem is with the Kleisli arrow. It's a nice little convenience wrapper that you put around your function. So if we have a function of A to I/O of B, then we get this Kleisli with its first type parameter is I/O, and its second is A, and its third B. We're going to wrap this one. Now we can say the F of Kleisli version and then the G of Kleisli version. We can compose those together. The compose function also exists, but I'm just showing and then because I like the way it reads. Now we get a Kleisli of I/O A to C. So we've taken the value B out of the I/O of B and passed it to the other function. And now we have a new function that is effectively A to I/O of C. So this gives us a way, and I'm probably repeating myself, of composing together effectful functions the same way we would compose together regular functions. So before I move on to the actual, starting to get into more meat and potatoes, any questions on this conceptual refresher? So the Kleisli lets us take a function of A to I/O of B and a function of B to I/O of C and get a function of A to I/O of C.
Yeah, How does it do that? There's some restrictions on when you can do that. So the and then I believe only works when the type of its first parameter here is a monad. So remember, monads have pure map and they have flat map. So effectively, what's happening here, and let me see if I can let me show some code examples because that might help. That is as soon as my compiler is done compiling. Let me stop pasting stuff into my terminal. All right, so I'm going to import cats. Come on. We're just going to do that data. All right. So if we have our, let me bring in one more. Hopefully you can see that corner there. Let me see if I can change the theme on this so that it's more readable. Okay, it doesn't look like I'm going to be able to do that, so let me just embiggen it some more. Okay, if I have some IO value, I can take a function, or I can flat map on that value and do something else with it, right? So what Kleisely's doing is it's taking my it's hard to type when my monitor's over here, so you have to forgive me. There we go. So given that IO is a monad, what we end up have happen, maybe it'd be better if I just show what the and then is doing. I think that's probably what we need to do. Okay, so yeah. There's our F. I'm going to define our G real quick. So what the Kleisely and then is doing is it's making a new function, fg, and it's defining that with a as the first parameter. It's running f. It's flat mapping on the results of f, and then it's running g. So that's what it's doing. So now if I provide a value to this new f of g, we get, if I actually run, let me actually run it, there you can see the answer is 60. The reason that's important though is because I don't really want to be writing that code everywhere I want to put two functions together that happen to be side effectful. So this gives us a nice convenience. So instead of saying all that, I can say, if I can spell Kleisely, F, then I could say res 3, and before I give it a 4, now you can see the result is 60. So What that also grants us, though, is the ability to treat our functions like they're monads. So in addition to there being a and then function, you also get just a simple flat map function. So if I say res3, which is a Kleisli, I can perform an additional operation on the return of that Kleisli. So I can say, let's add 100 to that. And then I'm gonna go ahead and run it with 4. Oops. Oh, I don't need a flat map because I'm not doing an IL. We'll just do a map. So I'll see res 8. I'll pass 4. Let's say if we're on sync. And there we go. It's now 160. So by being a Kleisli, not only do we get the nice function compositions, but we can also just treat it like it's any other monad in Scala, like a list or an option or a future or an IO or a promise. We now pass this along. Sometimes this is called a reader monad. That's another name for it. But we can talk. I can do another presentation another time where we talk more about monads. Did that help answer your question? Okay, awesome. So I'm gonna exit that console. Okay. Any other questions regarding any of the conceptual things we just got a refresher on? All right, let's talk about AWS Lambda. That's kind of the point of the talk today. I just wanted to refresh because I'm going to be using some of these concepts later. So AWS Lambda is what's called a function as a service. Some people also call that serverless, but quite frankly, that name annoys me because it's just other people's servers. It's like the cloud is other people's computers. It's a way to execute some code in response to some events. So it's not like your classic, I have a computer running that can listen on TCP ports or anything like that. AWS Lambda is a lot more restricted in what it can do. So, but what can it do? It can listen to these kinds of events. So in AWS, we can listen to simple queue service messages, any DynamoDB updates, S3 uploads. We can listen to HTTP requests by using the AWS API gateway. That little IoT button that you probably saw in the restroom here operates using AWS Lambdas. So it can, or at least you can hook that button up to an AWS Lambda. So it can, any of those events. So why would one bother doing any of this if it's limiting? Cost. The big thing is cost. When your Lambda's not running, you're not being charged for your Lambda. Plain and simple. So it's a big cost-saving thing. An EC2 instance, if you were to keep it running all year, would cost you quite a reasonable amount of money. So you only pay when your code is actually running. The other reason, besides it being cheaper, is AWS Lambda functions are more elastic. So we're talking about auto-scaling up and down without you having to think, is there going to be a big load this weekend? Do I need to scale up more servers? Or let me write a bunch of infrastructure code to detect when my servers are starting to get overrun so that I can start up more instances or something like that. That's not a concern with AWS Lambdas. You can have as many functions running as you need to meet your load. They do supply some throttling support if you want to put an upper cap on your actual usage. So you don't have any bad actors causing you to get charged $1 million for running 10 billion Lambdas or something. The other thing is maintainability. You don't have to maintain a server anymore. You don't have to worry about its infrastructure or anything like that. So it kind of simplifies some stuff. You don't have to worry about server updates. But mostly it's cost, right? Let's be honest. All right, so why not fast though? With all those great things, we know that there's some limitations. The first thing is latency. Amazon has done a lot to reduce their latency, but in my example, my Scala app that I'm going to show a little bit later, it takes 20 seconds to cold start, which is not great. There's some things I'll talk about at the end of my presentation to help fix that I haven't gotten to yet, but latency can be the cold start time can be an issue depending on your language. Node.js starts up real fast. Some of the native stuff starts up fast, but depending on your specific runtime, latency startup of a Lambda might be bad. They're limited in the amount of duration an individual Lambda can run. So if you need to be hooked up to like a Kafka queue continuously listening to something, because Kafka is not one of the events you can do, you really should be using an EC2 instance instead. If you need to process data that takes a significant amount of time, AWS Lambda might not be the right place to do it unless you do some tricks with like doing part of the load, sticking the rest on an SQS queue or whatever. So the time limited nature of a Lambda run might be one of those things you got to consider. Debugging and profiling them can also be kind of painful. Because if you think about it, you don't have a way of attaching a C debugger or a Scala debugger or what have you up to it. There's just not a way to do that. So you can't just attach a debugger. And with AWS Lambda, there's a little bit of an issue maybe getting vendor lock-in. If you start using their DynamoDB and the API gateway, you're going to start getting their tendrils all up in your code. There's some things you can do about that, though. If you keep everything at the edge, you'll probably be fine. But these are just some reasons why you might reconsider a FaaS. So what is this API gateway thingy I've been talking about? So it's an API gateway, which is exactly what that means. It's think of it as like a more specific purpose Nginx. So it's for REST APIs, and it is a way of proxying HTTP requests into stuff inside of AWS or outside. So here's some of its features. You can get monitoring through their CloudWatch service, which is something you can also do with your Lambdas. So I'll show that later, but your Lambdas, all of their outputs get logged. It's very scalable. So one thing that Nginx doesn't do for you is auto scale, right? You'd have to scale your Nginx if you're getting tremendous load, but API Gateway is serverless. They've got a lot of instances that'll scale as big as your needs. It supports WebSockets. It's got its own built-in security controls, caching. You can proxy your EC2 instances, your Lambda, or any VPC or private data center or whatever. So their API Gateway is fairly powerful. All right, so why Amazon, the Gateway and the Lambda? Because really, if you're wanting to call your Lambda function, which is for an HTTP request, your Lambda function is gonna end up being some HTTP request to some HTTP response. That's basically what a web server boils down to. So we're just gonna make our Lambda function not worry about routing or TCP or anything. We're gonna boil it down to some JSON request that the API Gateway is gonna hand us. This request has information in it about the path that you were called with, what HTTP method, any of the headers that were passed to the gateway. The reason why there's two of this is because sometimes you can have multiple of the same headers, and so the second one supports that. Any query string parameters or multiple query string parameters. And then it breaks up the path parameters and gives you some AWS-specific request information. And then the body of the request they send you is in this string payload. So if they send you JSON, you get it inside of a string. It's JSON encoded in there. If they give you a XML document, it's going to be XML inside of that string. What's fun, though, is what if you need binary data in your Lambda? What if somebody's loading images into your Lambda and you want to do image processing? Well, that's what this is-base64 encoded flag is for. So if you send binary to the API Gateway, it's got a base64 encode it, set this to true, and then this will be a base64 string containing your binary data. So this is the input to our Lambda function from the AWS API Gateway. Anybody got any questions on that? All right, the request format is a little big. The response format's a lot shorter. So the same base64 encoding applies. If I'm sending out binary data, I need to base64 encode it before I send it to the API Gateway as my return. And so my body will, just like before, it'll be either JSON or XML or whatever, and if it's binary, I have to base64 encode. You get your status code as your response, and then the headers are multi-value headers. So there's not as much data you got to send out as you're getting in. All right, so if that's what AWS's Gateway is sending us, how is any of this working? Well, if I'm operating on the JVM, I have a function that looks like this, that the AWS API Gateway is going to trigger my function, and then that request JSON body is going to come into this Java IO stream, and then my response is going to get written to this Java IO output stream. So, couple things. AWS provides a lot of SDKs for Node and Python and Go or whatever that abstracts a lot of this away and will just give you an object that contains the request. But I wanted to look at what actually is going on under the scenes. which is why we were talking about the actual JSON, right? The other thing is I wanted my Lambda to be as small as possible, so I didn't want to add any dependencies on the AWS SDK. I wanted kind of the bare minimum. I wanted to do it myself for the experience. But if you're in Node, they'll abstract a lot of that away from you. If you're in Java and you don't want to do it my way, then they'll abstract a lot of that from you. But this is what it is. And I wanted to represent it as it's a function of some input to some output. Okay, let's talk about HTTP4s and some about it. So first of all, it's a functional web server for Scala. It's a type level project, so it's part of the CATS ecosystem, and I happen to be one of its contributors. I've contributed to it and one of its side projects, Row, which I highly recommend both of them if you're in Scala. They're pretty awesome. I'm not just saying that because I write some of it. Okay, here's the anatomy of an HTTP4s app. And the whole reason why I talked about the Kleisli thing. An HTTP4s app is a function of request to some effectful response. That's it. Okay, there's a lot of code to make that happen, but the basic plumbing is I'm serving up a request to response function. Most other platforms that I can think of, like Play Framework or Spring Boot, they're operating on MVC. So there's all these controllers, and there's no clear place where the entry point is. I mean, there's a main function that they're executing somewhere that starts up some TCP sockets and whatnot. But for an HTTP4s app, I'm just this function. It's nice and simple. So we're a Kleisli of F. The reason why there's an F on the request is because the request bodies themselves can be effects. Same with the response. Okay, so that's the app. Now, one thing that you don't notice here is what happens if I'm writing some code that I don't, like I'm writing a router and some of this router, maybe not all the routes will match. If I'm operating on an HTTP app, then this thing must match everything. So I've got to return like a 404 for stuff that's not found. So what we have here is the HTTP route, so I can write subparts and then compose them together in the end. So these subparts are encoded as a request to some maybe response. So now I can compose multiple routes together, and then in the end, just say if any of them were optional, or if I got an option back when I ran my request, return 404. So I can compose a bunch of these together and then ultimately get one of these, and there's my function. Okay. Doesn't that request to response look a lot like AWS Lambda? Right? Because that's what we have. So how do we convert an HTTP app into a Lambda function? Is it? Oh no, I'm highlighting everything. Thank you. All right, can we still read this? We good now? Okay. All right, so doesn't that though look like a Lambda function? Some request, some response. So how do we convert the HTTP app into a Lambda? First, we read the request from the input stream. Then we run the HTTP app, whatever it is. Then we write the response to the output stream. Cost savings. Okay. So let's see some code. Let me move some windows around here and see if I can't make this. I guess I can't make the side panel bigger, but I'll do what I can. All right, so this is a standard Scala project. I've got my SPT version, a bunch of plugins that make things nice and easy. I've got this build configuration, but this is all details here. I have a script to build my database tables, a great binary piece of data for an example. All right, and then this. So one of the things that I did, in this example, source code, I'm gonna it's already on GitHub, but I'm gonna make it a public repo after the presentation. So if you miss anything and would like to look at it in more details, be my guest. For the example, I used a framework called serverless. Has anybody heard of the serverless framework? There was a talk on it, I believe, last year at 200 OK. Basically, though, I'm just specifying some things like I want everything that matches this to be binary for my example. I've got some plugins. I'm using AWS, the Java 8 runtime, 512 megs of RAM. I'm putting it in US2 West. I'm setting up some IAM stuff, blah, blah, blah. Environment variables. This is where my artifact is, so when I compile my code, this is what gets uploaded. And then here is saying what my function is. So that entry point that I showed you earlier, that function is specified right here as that handler. So when I show my example code, you'll see in the package hello to do, there's a class called Lambda entry point that has a function called handler. This is what's going to get called by the API gateway. I got a 30-second timeout, so if my function takes any longer than that to respond, it cuts it out. And then all the rest of this is just some CloudFormation stuff that Brad here helped me with to set up a database and set up all the VPC stuff that I needed to make this happen. All right, let's look at my entry point. So here's my setup. This, you know what, let me change themes here to make this maybe a little bit easier. I should have thought of that beforehand, but I think solar is probably not the best. Let's go with one. Is that easier to read? All right. So here in my trait routes, I basically am just setting up a database connection from the environment variables that are provided in my Lambda function. Then I have this function routes, which is my HTTP app. And what I'm doing here is I'm printing that I'm setting the routes up, and I'm getting my database connection ready. I'm creating one of those row routes, which are related to HTTP routes. I'm generating some Swagger documentation for them, creating another service. And here I'm composing the two row services together, getting their Swagger docs into a special Swagger route so we can actually see what our endpoints are. And now I have two sets of HTTP4s routes. I'm using the special operator that is basically the and then, or it's not the and then, it says this Kleisli that returns an optional response, compose it with this other one that returns an optional response. So if this one comes up with none, then it tries calling the second one. So I'm combining those routes into one set of routes. Then I'm saying if any of those come back with, or if all of that comes back with none, give me an HTTP not found, and I'm turning cores on. So I'm using the cores middleware here. One of the things I should note, because I know I made a big thing about the Kleisli and how cool that is. Part of the reason why that's awesome in HTTP4s, besides the ability to compose them together and join them like this, is also because their authentication framework in HTTP4s, they make it so that you have a function of request to user, and then your routes are a authenticated request to response. And there's a function that puts those together. So it'll call your authentication, it gets the user from the request, and if the user comes back, then it will compose in, it'll pass it as an authenticated request to the other half. And when you put those two pieces together, you end up with the HTTP routes. So you end up with an auth routes and a user service to an HTTP routes, and it just kind of hooks together through that Kleisli system. All right, so now we've got our HTTP app. Here is our HTTP4s entry point. So this is an IO app with those routes from above. And just like a standard Java app, this is basically public static void main. I have some type arguments, and I'm returning some exit code. I'm starting up a Blaze server on port 8080 with my routes, and I'm exiting. So this, and part of the big reason why I think this is cool, is with HTTP4s, I can still run my Lambda function as a standard web server locally for when I'm testing. Because remember, part of the downsides of AWS Lambda was it's hard to attach a debugger or a profiler to figure what's going on. But with this, I can just take what I was going to run as a Lambda function, run as a standard HTTP server, do all my local development super speedy, just like I normally would, And then when I'm ready to launch it as a Lambda, I just do this. I have this Lambda handler class that I'm extending. I've got my routes, and my entry point here is run some IO of HTTP app and routes. Now it will run as a Lambda function. Okay, there's a lot of code behind the scenes to make this happen. Let's start looking at that. By the way, I will be open sourcing this code, so it'll be available to everybody. But I guess before that, let's look at what we actually have here. So we have the to-do service, which is basically just has a list of to-dos. You can create them, you can complete them, you can delete them, etc. And it connects to a database. Here's our database model, and we're running some queries, standard stuff. Let's look at this Lambda handler. So that entry point is this abstract function that we're asking our users to define, and we're going to say, you give us some IO of HTTP app. And the reason why we're saying an IO of HTTP app is because if you remember my setup code, I was setting up a database connection for my Lambda to run. And one of the implementation details that they don't tell you about AWS Lambda is there's the cold start and then there's the hot start. Cold start is when it actually has to start up a JVM, load everything into a Docker container or however magic they're doing it, and everything has to start up. So that, for my app, takes about 20 seconds. Not ideal. But during that cold start, I wrote it so that I can take and connect to my database, and then I can store those database connections. So when the next call comes into my Lambda function, it's going to do a hot start, which means it's just going to execute that entry function again, providing some new input and output streams. And since my JVM is there, I basically have a global variable where I'm storing my database connection for the next call around can reuse that connection. And since we're trying to do everything pure functionally, that global variable, if you will, is that creating and setting of that global variable is encoded in my effect type, the IO here. All right, and this is just some stuff to get some context shift and timers for our app to use. But let's go to, here we go. I should have put a new line here. Here is our handler function, our input stream to output stream. We're gonna first convert the input stream to a request. While at the same time we're parsing that input stream, I'm going to execute the IO that our routes are in, and I'm going to memoize it. That way, next call, the values stay here for somebody to use. So this is already memoized, and this is just going to trigger that so it gets cached. And then I'm going to execute that route, or those routes that the user specified with our request. Then I'm going to take our response, and I'm going to run it through that output stream, and I'm going to execute all that. Because I still have to return a unit, so I'm going to execute it synchronously. This handle's got to wait until I've finished writing to the output stream. So here's our input stream request, or input stream to request, and this is just FS2 parsing an IO stream to some JSON, and this is just doing the opposite. Here is our proxy request. So you saw the JSON, the kind of sample JSON for this earlier, but there's the example of it. Here I'm doing the base 64 encoding. If it was base 64 encoded, I'm going to decode it properly, etc. Down here is our proxy response. And what I'm doing is I'm detecting if the content type is binary. I'm going to base 64 encode it before I send it to the server. If it's not, I'm just going to write it out as that string. And then my JSON framework will convert it from a string that contains JSON, will properly escape all the characters if it was JSON, etc. Any questions on this? I guess I kind of sped through that quickly, but the thing that I loved about this was that it only ended up being 150 lines of code. I went and took a glance at this. There is a project for taking a Spring Boot app and running it inside of an AWS Lambda, which is probably not great because I know Spring Boot can take even longer to start. But I went and looked at the code to do the same thing, and it was a lot of files with a lot of lines of code. But I managed to get full support for binary and textual content types. multi-query string parameters and all that for HTTP4s and under 150 lines of code. So, I mean, not bad, right? And it's because there's no impedance mismatch. We're not, oh, I gotta find all of the controllers and then do some wiring up or whatever Spring Boot's doing. It's just a function of request to response. So all I had to do is translate one request into my request and then translate my response into another, and it was done. So now that you've seen the code, let's see it in action. Let me pull this over here. And, well, first, I'm going to, because I said we could do this, I'm going to go ahead and start a local server. And there's my local server. And show you there is the Swagger JSON from my local server. And you saw how fast that started up. I can go to do's and get out a error message because I forgot to start up my Docker container. Let's start that one up and then start up that Postgres. At least this way, since I'm locally testing, I can get my error messages really well, and I could have attached a debugger if I needed to. All right, while that's starting up, let's... Okay. So here is my Lambda function out in AWS. So that's the path, there's the region, it's in the dev scope, and you can see it's cold starting right now because it's been maybe an hour since I hit it last. Fortunately, there are ways to keep your app warm by using some serverless plugins or there's a scheduler you can have in AWS to hit it frequently. And it timed out because it took more than 30 seconds to start, so let's call that 40. We'll hit it one more time and it should...
Keeping things warm, is that negligible cost-wise?
So they have a certain duration of time that will leave your Lambda function in memory. And even if they're leaving it in memory, it doesn't cost you anything. What costs you is the execution time. So what I've seen is the pattern of making a keep warm route that basically does nothing but return OK. So it's relatively quick. And then if you call that every once in a while, it's going to be one Lambda execution. It's going to take a couple hundred milliseconds of time. So your cost will be relatively minimal. And then you won't have to worry about this demo-itis I'm experiencing right now. So while that is solving itself, which it should do shortly, let's look at the... So this is the designer in AWS. So when I ran that serverless YAML that I was showing you earlier, it span all this up. It loaded my jar file into an S3 bucket. It created the API gateway, set up the subnets for the database, etc., and all this. Then the CloudWatch. Let's see if I can go look at the CloudWatch logs. CloudWatch. Here we go. Give that a second and then go again. So you can see here is the logs of my service. And one of the nice things they'll do is they will give you a request ID. They will log out every time it starts. You can see here's that setting up routes message that I printed. Gets put in the CloudWatch logs. And then there's the end. So not too much there. That's great. And you can see it started, setting up routes, ended, and it took more than 20 seconds. So I'm going to live tweak this timeout and see if I can't get it to actually work. So I'm packaging up my jar file, just making sure I had it. did I do? So now I can say serverless deploy, and that is going to take that jar file and it's going to redeploy it out there, and it's going to set my timeout to 120 seconds so that hopefully my abysmal cold start time is okay. You can see my jar file in this instance is 40.88 megabytes, which is less than ideal. The bigger the jar file, the longer it takes to upload it to S3, so you can see how long it's going to take to do that. And also the longer it takes for the Lambda system to pull it from S3 and to start it up itself. So I've been thinking about this cold start time, and while that's running, we'll move back to some slides, assuming I can find them. Here we go. So some possible improvements. We could reduce that jar file size, which is currently 40 megabytes. Two ways to do that is, one, we could use AWS Lambda layers, so we could put some of our dependencies in layers, and that should reduce the number of dependencies that have to be in my specific Lambda. I haven't tried this yet, so I don't know how much improvement you'll actually get, because it may be that the Lambda layers themselves now have a little bit of a time to pull those onto whatever server. The other thing is ProGuard. Has anybody heard of ProGuard for Java and Android? It is a system where you can take a jar file and reduce its size before you use it. It was designed earlier in Android when APKs, which are the jars of Android, could be only a certain size, and people still wanted to be able to use cool libraries so they didn't have to reinvent wheels. So they have, and also so that they could obfuscate their code, they wrote ProGuard. And so it'll take your jar file, strip out anything that it's detecting is unused code. That means removing entire sets of dependencies that aren't used, and it'll also obfuscate so lots of dead code elimination and obfuscation. You can turn the obfuscation off, which is what I was doing. But yeah, I tried it a little bit with mixed luck, but I know with the right settings, you could get ProGuard to trim the right stuff so that your app will still work, and your jar file will be significantly smaller, because I'm not using that much code if you do dead code elimination. I got a bunch of dependencies that I'm using 1 or 2 functions from. So we could get that jar file probably down to 5 megs if we ran it through ProGuard. Another option is by using a faster runtime. So JVM is kind of slow on the start. AWS has done a lot to make it faster, especially hot starts, but let's just be honest, JVM, kind of slow. Hopefully they'll support Java 11 soon, which will solve some of those problems. It starts a lot faster. But in the meantime, with Scala, we could possibly use Scala Native or the Graal VM, which is another virtual machine for Java that has a faster warm start, because AWS now supports you to set up your own runtime. So we could use Graal and run Scala on that, and that should be better. Or Scala.js running on Node. Since Node has a very small uptime, it would be possible to do that. I haven't looked into what it would take to get Http4s compiling in Node just yet. I know there's some PRs on it, but it might be a future project for me to get some faster Lambda start times. The other thing is that keep warm that I was talking about earlier. If you keep your cold start, if you keep it warm, you don't have to worry about cold start as much. But here's one of the downsides of the AWS Lambdas. Each of those Lambda functions will only run one API gateway request at a time. Even if it's running on a machine with a lot of RAM or whatever, it only runs one request at a time. And for the apps that I write, most of the stuff that my code is waiting on is I/O wait. So I could have that one Lambda function doing a whole bunch of stuff, but it's just a limitation of the way the API gateway works. So when it starts scaling, it's going to start having cold starts, because I'm running one request. Now if a second request comes in, and there's only one Lambda warm, that other one's gonna cold start. So you need to keep several of them warm, or you need to reduce that start time. Another thing to improve performance is I'm using Postgres, which is not ideal. There's a connection limit to Postgres servers, so if my little to-do app scaled up to hundreds of thousands of users, my Postgres would probably start grinding to a halt. But Amazon has Aurora, which is Postgres and MySQL compatible serverless database system. So you can scale that up as much as you want. And then there's Amazon DynamoDB, which is a NoSQL database, but it's also serverless. So it scales pretty intensely. So let's go back and see what's happened here. So it looks like it's deployed now. Let's see if I can get that Swagger doc to load. While that's loading, though, does anybody have any questions? Yes.
Have you tried increasing your RAM with the cold start?
It was initially 1024, but it will log in the CloudWatch. It will log your app's actual usage. And so you can see memory size 512, used 232 megabytes. So I had it at 1024 and I didn't want to accidentally get out of my free tier, so I just reduced the RAM just to make sure I stayed in the free tier. But it's possible that increasing it to 1024, even though it only used so much, might increase or decrease this time for a Java app.
I always say that because when I wrote a Lambda function in Lambda, increasing my RAM, I increased my RAM to 2 gigs, and cold start time basically vanished.
Okay, so let's. The question was, have I tried increasing my RAM size in order to decrease the latency? And the answer was, I actually decreased my RAM size. So let's, I changed it in the serverless config, but I'm going to go ahead and just move that up, save it, and then give that another try and see what happens. It'll probably work this time. Any other questions while we wait for paint to dry? Hey, look at that. So now that I got the Swagger doc, let's go ahead and pop it into the pet store Swagger IO. So you can see this is the service that I wrote. And just for show, here's my list of to-dos. There you go. I even have a smiley face in one of them to show that we can support UTF-8 emojis. I had to binary encode the JSON using that base 64 to make that work. Here's some XML. I wanted to show some of these examples because I wanted to make sure, so that everyone knew, just because those requests and responses from the gateway are coming in to my app as JSON doesn't mean you're restricted to JSON format coming in and out of your app. Here's a test for binary, which doesn't work very well in the Swagger, but if we come over here and actually, whoop, that's not going to do it. There you go. So that just came from my Lambda function. And note, now that it's warm, it's really fast. Also, thanks to Hans' suggestion for increasing the RAM size, I'm sure that helped quite a bit. Okay. Now if we come over here, we'll see all those executions I just did in the CloudWatch. And they have a cool dash. Let's go to the metrics. Lambda. That wasn't what I wanted. What did I want? Here we go. So you can see the responses coming in through the API gateway and their latency, incoming log of requests. There's my error rate. You get all sorts of cool stuff for free. There's my actual CPU utilization. You see basically nothing. All right. Any other questions? Awesome. Well, all this is on GitHub. I'm going to flip it from a private to a public repo here in a little bit. And I will put the link in the Slack channel and in the meetup if you're curious, and in the YouTube link for those who are watching remotely. So if you're interested in the code, you can look. I want to say thank you everyone for coming. And I also want to give a shout out to this guy's repo here, Howard John. He actually wrote some of this. He wrote something very similar to what I wrote. In fact, I borrowed some of his code. But his was a little more generic because he also supports Akka HTTP, another framework in Scala. And I just wanted to just do the Http4s parts, and I had a little differing opinions about some things. So I did it myself. But I want to give a shout out because I borrowed a lot of his ideas and code, and it was kind of the inspiration for doing this talk. Because I first started scratching my head when somebody told me about API Gateway of whether or not it was possible. And then I saw somebody did it, and I was like, well, I have to do it now. So, but all right, thanks everyone. And if anybody has something they want to talk about next month, ideas, please let me know. I will not be doing the talk next month, so please somebody else. All right, thanks again.